In this video, we're going to talk about the chain rule. The first thing to know is that the chain rule is used to find derivatives of composite functions. And here we have some examples of functions that don't require the chain rule and those that do. So if I take this first example here, I see that I have a function within a function. So the inner function is my x squared plus 1, and my outer function is this square root. So it's this function to the 1/2 power. And that's similar to something going on here. So the power, instead of being 1/2 power, is to the 5th. And this one here, the sine of 6x, that 6x is actually a function within the sine function itself. So here we have the formal definition of the chain rule. It essentially says that if you have two functions, so f and g, and they're both differentiable, and I compose them, so that's f of g of x, I can take the derivative of that, and this is the rule that I use to do so. Essentially, you have to split up f and g, and you take the derivative of f and you plug in g of x into that, and then you multiply that by g prime of x. So we're going to do a ton of examples, so hopefully by the end of the video, you have a better understanding of how to use the chain rule. So the first thing that you really have to understand before even applying the chain rule is how you can decompose composite functions. Essentially being able to find a function within a greater function. One way to do this is to take this idea here of what a composite function is and look at, if I have g of x as my new input, I could replace that with some other variable like u. And so really I'm looking to find f prime of u times u prime. And there's a whole bunch of examples down here, but let's just take this one. And looking at this quotient here, I have a function within a function. So that u function is actually the denominator, so x plus 1 we could redefine as u. And that means that if I apply that in terms of f of u, I get y equals 1 over u. So that will allow me to take the derivative of this guy first in terms of u, and then also to take the derivative of just u itself. And as promised, we've got a ton of examples to go through, so let's start with this guy. Let's take the derivative of this cubic function here. First thing I have to do is decompose my composite function. So this inner function here I'm going to define as u, so that's x squared plus 1, and I can take the derivative of that, and that's just 2x. And so that means this entire function in terms of u, or f of u, is going to be u cubed. And the derivative of that will be 3u squared. So here's my definition of a chain rule in terms of what I've got here. So that means that I can just plug and chug and figure out what this is going to be. So when I go to replace f prime of u, I'm actually going to plug in what I've defined as u up here. So that's going to be 3 times the quantity of x squared plus 1 all squared times our u prime, which is times 2x. I'm going to combine that 2x times 3, put it outside here, and this is my derivative of y. All right, here's our next example. So I've got g of t is equal to this quotient here. One of my options is to rewrite it, so let's do that. So I'm going to rewrite it as one line here so that I can just use a constant multiple rule. And so I'm able to define this as my u function, and this is my f of u function. So I can find the derivative of u and the derivative of f prime of u. And so let's plug all these things in, work them out, see what we get. So once I have everything plugged in here, it's just a matter of multiplying and simplifying. So I'm going to end up with 28 all over the quantity of 2t minus 3 cubed as my derivative here. So for our next example, we're going to need the product rule because I have f of x is equal to x squared times the quantity of 1 minus x squared all under this square root. So this is going to need the chain rule, and then these two pieces are going to need the product rule. First thing I'm going to do is take care of the derivative of this guy right here. So I'm able to identify u as this 1 minus x squared, take the derivative of it, identify f of u and f prime of u right here, plug it in, and I define this little bit as h of x. You can call it whatever you'd like. So the derivative of this piece is going to be this quantity here. So I'm going to use that in combination with the product rule to find the derivative of this entire thing. So let's do that on a fresh slide here. I've written out here in pink the derivative with the product rule of f of x. So that just takes this first bit here, x squared, multiplies it by the derivative of this second bit, and adds it to the second bit times the derivative of the first. So the derivative of x squared is 2x. So I've taken that one step further here, plugged in my h prime of x, which I found on the last slide, and I just converted this radical to this quantity to the 1/2 power. So what I'm going to do from here is simplify this term and that term as much as I can, and a cool little algebra trick is to pull out the quantity x times 1 minus x squared all to the negative 1/2, because when I pull it out of this term, it becomes 1, which is so much nicer to work with. And when I pull it out of this term, 1/2 minus a negative 1/2 becomes just to the first power, which is awesome. I distribute all that stuff, and this quantity becomes negative 3x squared plus 2, and I multiply it by the equivalent of this guy. I like to turn it into a fraction. You don't have to. And then this is my resulting derivative. Now for our next derivative, let's see what happens if I don't rewrite this denominator here and just leave it as a quotient using the quotient rule. So in decomposing this composition, I'm going to identify our denominator as h of x and then use the chain rule to find the derivative of h of x. So I'm able to define u as x squared plus 4 and f of u as u to the 1/3, take the derivatives of both of those, plug them in. I'm going to leave h prime of x like this, and so now let's use the quotient rule to find f prime of x. So the next thing I'm going to do is set up my quotient rule. I'm just going to use g as my numerator and h as my denominator like I did in the last slide. And so this is my quotient rule here and a reminder of my h prime. So let's plug in all the things that I have. So my first step is to plug in all the things from this definition and simplify as best as I can. So this is a simplification of what I have here. All I really did was multiply my x's together to get 2x squared, and I kept this the same. And I distributed the 2 to the 1/3, so it's the quantity to the 2/3. And what I'm going to do now is I'm going to isolate this term and factor it out. So if I divide something by 1/3, that leaves a 3 in the front, so that's why there's not one here, but there's one here, because 1/3 times 3 is 1. And so when I pull that negative 2/3 power out from here, it becomes a power of 1, which I can then distribute that 3 to in a moment. And when I pull out this term from the 2x squared, obviously that's just 1, so I'm left with just minus 2x squared here, which I can combine, which I've done in green over here. And I leave the denominator alone because you don't pull something out of the numerator and the denominator, you just pull it out of the numerator. And so I turn this into a fraction and I simplify this fraction and I multiply them together, and this is my final derivative. Our next example is this equation for y. So I need the chain rule here because I have this quotient, but it is brought to the second power. So let's see what we got to do here. So the first thing I notice when I break this apart is that u is this fraction right here, but in order to find u prime, I'm going to need the quotient rule, which we'll work out in just a moment. So f of u is just u squared, so the derivative of that is 2u, which once we find u prime, it'll be quite easy to do the chain rule. So let's work out u prime. So I substitute everything in from this definition and I distribute all the things and my negatives and I get this for u prime. So let's plug that in to find the chain rule to find the derivative of y. So I'm going to take this definition using the chain rule, plug in this piece, and I'm going to plug in u prime in just a moment just to save a little bit of space. But essentially my numerator, I'm going to leave in factored form, so that's my 2, 3x minus 1, this numerator here, all over x squared plus 3, all to the 3rd power, because I've got 2 here and 1 here, so this is my factored out derivative of y. Switching gears a little bit, let's talk about trig functions that apply the chain rule. So these little shortcuts here are the chain rule versions of trig functions. So notice, for example, when I take the derivative of sine, normally we have sine of x, and that would just give you cosine of x. But what happens when u becomes something like 2x? this is the rule that you would use. You would make u your 2x, and then you would have cosine of 2x, which applies this rule here, cosine of u, and then you would multiply by whatever the derivative of u happens to be. And in this case, it's going to be 2. So the derivative of sine of 2x is going to be 2 cosine of 2x. And you can apply those rules for something like these two as well. And I just want to take a moment to remind you about parentheses and trig functions. So here's a couple examples that walk through different things that happen with parentheses. So if I look at the first one, and I have this function cosine of 3x squared, I would imply parentheses around the 3x squared, so that would become your u, and you would apply your chain rule to that to find the derivative. And then if I look at this example here, the cos squared of x is like saying cosine of x all squared. So that means that cosine of x is your u. So you would take the f prime of u, like we've been doing, and then multiply it by u prime, and that's how you get the derivative using the chain rule of that trig function. Now let's work through this example. So let's say I have f of t is equal to sine cubed of 4t. The first thing I'm going to do is rewrite f of t. And I'll rewrite that as the quantity of sine of 4t all to the third power. And I'm going to make my u the sine of 4t because when I use the rule from the last slide, u prime becomes 4 cosine of 4t. And so I can also write my f of u, which is u cubed, and so the derivative of that is going to be 3u squared. So now let's put that all together and find the derivative of f of t. Now for f prime of t, I'm going to start off with the definition of the chain rule here, going to plug everything in, and really I just need to multiply my 3 times my 4 to get 12. And here is my derivative, f prime of t, or another way you could write it is take that little square and put it right here. It means the same thing. So let's do one more example problem, and it's a 2-part application problem. So let's take our function here. F of x is equal to 2 sine of x plus cosine 2 of x. So our first problem is to find an equation of the tangent line to this graph at the point pi comma 1. So essentially, we're looking for the equation of this blue line right here, which is tangent to that point of f of x. First thing I got to do is find the derivative of f of x. Using the rules that we already know, we can find the derivative of f of x to be 2 cosine of x minus 2 sine of 2x. And now that's going to help me find the slope of this tangent line right here. So I'm going to plug in pi for x and see what I get. So when I plug in pi, I'm going to end up with -2, which is the slope of this tangent line right here. So I'm going to take my point, my x1 comma y1, so pi and 1, and plug them into this equation along with our slope. And I'm going to simplify it to get the equation of our tangent line at pi comma 1 to be this equation here. So y equals -2x plus 2 pi plus 1. And just a quick reminder that 2 pi plus 1 is going to be our constant here. And now with the same equation, part B is asking me to find all the values of x on the interval between 0 and 2 pi at which the graph of f of x has a horizontal tangent line. And what that means is that our derivative, our f prime of x, which is also the slope of our tangent line, is going to be 0. So if I look at this graph here, this curve, this black curve, I see about this point would make a horizontal, so would that, so would that, so would that. So we're probably going to end up with a handful of points. All right, so the first thing I'm going to start with is I'm going to bring back my f prime of x, which is 2 cos x minus 2 sine 2x from part A. Now before I even set this thing equal to 0 here, I'm going to replace sine of 2x with its counterpart in basic trig equation rules here. And if you don't remember your double or half angle rules, you can look them up on the internet. They're even in our textbook. So I'm going to replace that with 2 sine x times cos x, which allows me from here, once I set it equal to 0, to factor out a 2 cosine of x, which leaves me with 1 minus 2 sine of x. So I'm going to set that equal to 0 and that side equal to 0 and find the values of x, where cosine of x is equal to 0 and sine of x is equal to 1/2. So in the interval from 0 to 2 pi, that's going to give me pi over 2, 3 pi over 2 for cosine, and then pi over 6 and 5 pi over 6 for our sine. And those values actually line up with our x values here, where we indicated that these points we're going to create horizontal tangent lines. And this last slide here is just to summarize all the differentiation rules that we've talked about in multiple videos already. So if you want to take a screenshot of this or find it in our textbook, that would be great to put in your notebook. All right, that's going to do it for this video. Thanks for watching.